In section 4.6, we're ready to model data with some quadratic regression. So we're going to determine those quadratic regression models and do some problem solving with quadratic regression. Okay, in our first situation, we're looking at the heat index as a function of temperature. And so we're going to first want to see a scatter plot of this data and decide if it appears to be quadratic. All right. So I got the data already typed, so you don't have to watch me type it. I'm going to go ahead and zoom fit on this data. And it's kind of straight, so I might be thinking linear, but there's a little bitty curve to it. There's a little bitty curve, so we can actually compare those two models if you'd like to see if linear or quadratic is going to do a better job. It's not really enough of a curve to make us think the exponential is the right choice, but there's a slight curving to this data. So maybe might be my answer that I can see from this data set is maybe quadratic. I'm noticing a slight bend or curve to this data where it's not exactly straight. So we'll make a note of that we're seeing data points where there is a very slight curve. So we're going to say maybe quadratic as opposed to linear because there is a very slight curve. Oftentimes it's more obvious than this one. It doesn't have to be obvious in all of them. So we're going to try to do the regression. Now we already know how to do linear regression, so we'll do that one first. Just going to make ourselves a note over to the side here that we know that if we wanted to do a linear regression, we do y1 approximately mx1 plus b, because a linear equation is usually written in the form y equals mx plus b. So if we want to do a quadratic regression, quadratic equations are usually written of the form y equals a x squared plus bx plus c. So y1 is approximately a x1 squared plus b x1 plus c. So ax squared plus bx plus c, replacing y and x with x1 and y1 respectively. So let's go ahead and do both of these just to see what happens here. y1 approximately mx1 plus b. Not too bad. I mean, it's as a model, it's quite good linear model. And then we'll compare it with our quadratic. y1 approximately a x1, oops, I hit the wrong key, x1 squared plus bx1 plus c. All right, so there's that slight curve I was talking about. I could see that slight bending as the data was increasing, and so the quadratic model does fit this data set better. If I was given the choice on this one, linear does a really good job. 0.99 is the error squared value, so you're not going to be that far off. But the thing is, on this one, I'm closest on the center points. I'm furthest on the end points. So linear would do a decent job making predictions for interpolation, but I'm already furthest off on the outer 2 points, so I'd be maybe worse off for the extrapolation. So out of these two, closer, it's particularly closer in the endpoints in the linear model would tell us that we'd be able to get a few years more of predictions, perhaps, based off the quadratic model than the linear model, because we seem to be fitting a little bit closer. So it's a quadratic model, as we can see here. Okay, so we got our model, and they want us to write it for number 2, do the regression equation, write our model. So our equation, heat index H, so H of T, what's our A parameter? I gotta scroll down. Our A parameter is 0.095, and then T squared, plus our B parameter is negative, so it's going to be minus 12.595 T, and then plus our C value, which is 483.875, or 857, I meant to say. There we go, 857. Okay, so hopefully those match up with what we're seeing. I just rounded them to 3 places because I don't think they told me, so I picked 3 places. Okay, so whenever they ask you to use the regression to find the model, write the model. Okay, write the model. We need to know what the model is. That's the model. And now I should type this model as well so that I can use it to make predictions. So h of t is 0.095 t, I hit the wrong key, t squared, and then minus 12.595t and plus our 483.857 there. Okay. Okay. So one of the things I noticed right away is that there seems to be a kind of large discrepancy between what I have typed right here and what is showing up as the red line for the model. So that's likely due to some rounding. So the most significant digit, no, most significant place value is the place value of the highest degree. So likely I need to up the accuracy on this one because I only have two significant digits. The 0 in front of the decimal, in front of the 9 doesn't count as a significant digit because there are no numbers in front of it. I'm going to up and put a 2 after it, and look how much better that is. Now I've actually got 3 significant digits on this number. So let me go ahead and sneak that 2 right here as well. So I thought I could round to 0.95 until I saw and I was like, oh, there's a pretty big error. I'm going to want it to be a little closer, so let me sneak that too. Okay. Now, how does the plot of the quadratic regression equation compare with the scatter plot? And it's super fine. So it's very close to the data set. Okay, so do we believe that this is a good model? Yes. And this can be confirmed because it has a very high r-squared value, and the r-squared value is 0.9998. You can't get a whole lot closer to 1 than 0.999 something, so this is very close to 1. Very close to 1, as I said. Next, they're asking me the practical domain of this function. So the inputs for this function are temperature in degrees Fahrenheit. And they do note that heat indices are not usually calculated until the air temperature reaches 80 degrees Fahrenheit. And so 80 degrees is going to be the smallest input that we're going to use on this one. We're not going to compute the heat index for something below 80 degrees. It's just not going to make sense. No, they ask us to, but we're going to see when we do that prediction that, yeah, it doesn't make sense because heat indices just aren't usually calculated until the air temperature reaches 80. All right. Now, I just need to top out what I think the temperature might be. So in the chart, it went up to 92, but we know it can get hotter than that. I'm going to pick like 102 or something, just to say, I mean, in Michigan, it doesn't get hotter than like 100. And other states, perhaps you'd get hotter. I'm using what I know from my experience. We'll say we're around here, and 102 might be the maximum value we're going to use. All right. So you can make your maximum value whatever you are comfortable with in terms of hot temperatures. All right. Now, prediction. Again, this whole situation was about 90% humidity. This is the formula that gives us the prediction, the heat index, if there is 90% humidity. So we want to evaluate H at 45. So what if it's 45 degrees? What would this formula report as the heat index? So H of 45 would give us a heat index of 109.9 degrees. Okay. And then H of 85 would give us a heat index of 101.1 degrees. And H of 100 would give us a heat index of 176.4 degrees. Now, when you're looking at some of these numbers, we should be thinking, no way. So part B asks us, which, if any of these estimates, do you think is the most reliable? So the only one that's likely to be reliable is the middle one. No way, if it's really 45 degrees, does it feel like 109 degrees? That one does not make sense, and it's clearly outside the practical domain. So that one does not make sense. Now, we had originally decided that maybe 100 would be in the practical domain, but now with additional information, h of 100 is 176. That's not true either. You're never going to say it's 100 degrees, but man, it feels like 176 degrees because you would not make it, that we would die. It's too hot. Okay, so the only one that makes sense is the h of 85 prediction. Okay, this one makes sense in the context. So if you're outside with 90% humidity and it's 85 degrees, it might feel like 101. So that one makes sense in context. Now, that's also the only prediction that's interpolation. Okay, so just as a note, this is also interpolation, and interpolation predictions are more likely to make sense. Now, with the knowledge that 100 does not make sense, you might be able to shorten your practical domain and say, I don't know what the upper boundary is, but we can probably go maybe to 95 or something. We'll shorten it because 100 didn't make sense, so maybe we wouldn't go quite that high. The table went to 92, so maybe we could push it a few more digits off, but we could tighten that down just a little bit because we now realize that it does not make sense up at 100. Okay. So continuing on, assuming that the relative heat index is still 90%, relative humidity, I meant to say, estimate the temperatures for which the heat index is equal to 100 degrees. Okay, so that's output, right? Output of 100 degrees. And it says use the given table, so that's the numerical method first. Okay, so my outputs are going to be 100 degrees. You know what? We're kind of close right here at 84. And then by 86 or to 105, 100 is closer to the 84 side. So maybe 84.5 degrees or something like that would be my guess based on the table. So I would guess approximately 84.5 degrees would give me an output of around 100. Okay, just a guess based on the information I see there in the table. I don't think 85 because I think that that would be a little high. I don't know. We'll find out. Okay. Now we're going to base off of the equation, so graphical. We'll get some more precision here. 100 this time is the output, so y equals 100. Let me turn off the actual regression line just so we can intersect with hit this point. Oh, graphical, we're like 84.69 or 84.7. So we're kind of close for the numerical. But graphical, we're going to get a guess of 84.69 degrees. Then algebraic, so using the quadratic formula. Okay, so I need my A, B, and C values, and I need T is equal to negative B, so negative 12.595 plus or minus the square root of B squared, so negative 12.595 squared, minus 4 times A, which is 0.0952, times C, which is 483.857, all divided by 2 times the A value of 0.0952. Okay, so we're just going to plug that all in because we're only looking for a decimal. We don't really care about simplifying, and they don't need us to. There's no space to simplify anyway. So fractions start off now. Negative 12.595. Now we have to do the plus and the minus separately, so we'll write the plus first, then we'll copy paste and do the one with subtraction. Okay, so minus 4 times A. What was A? 952. And C, 483.857 divided by 2 times A. Okay, hold on, something did not work. All right, so let me make sure that I have my values typed. I know I did. Okay. Oops. Okay. So we got to fix just one little bit of this. So when we were doing our equation, we were looking for when 0.0952t squared minus 12.595t plus 483.857 is equal to 100. And when we use the quadratic formula to solve something, we have to get it equal to 0. I forgot that we're solving for equal to 100 here, and I have not yet subtracted the 100 off. That is an important step. As we just noticed, it did not work when I forgot to do that. So this would give me 0 equals 0.0952t squared minus 12.595t. 483 minus 100, that's going to be plus 383.857. So we're going to go over here into our equation and change C to 383.857. Right. So back over here, if I just change this number for C, there we go. And we get 84.69. Now I can copy and paste this and get the negative 1 also. I didn't get the other one before because it's outside the practical domain. And so it's going to be a value that does not make sense. So I'm going to make a quick note of these. From the addition, I got the prediction of 84.69 degrees and 47.61 degrees. But of course, that second value is outside the practical domain, and so we're going to focus on that first value. If it's 47 degrees, it does not feel like 100 degrees. So maybe if it's 84.69 degrees, it might feel like it's 100 degrees. Okay. So sometimes mistakes are helpful because we remember important things we need to make notes of for ourselves, that we are actually getting our function equal to 0 before identifying a, b, and c and going into the quadratic formula. It's got to be equal to 0 before you can enter it into the quadratic formula. All right, so how did the results compare? Well, the numerical method sucks, and the other two methods are good. So the graphical and algebraic methods give us the same thing. We never use numeric if we need an actual answer, but it can give you a ballpark idea so that you can tell if your answer that you do get from graphical or algebraic is in the vicinity of the right answer. So yeah, I mean, it tells us that yes, our answer makes sense, right? Our answers make sense because the table was showing that it should be somewhere in that 84 point something range. Okay, so number 7a. In 6b, the stated relative humidity was 90%. We wrote the equation to determine the temperature for the heat index was equal to 100 degrees. Write the equation to determine for which the air temperature and the heat index are equal. All right. So in 6b over here, we had to write the equation for when the heat index was equal to 100 degrees, as they are saying. Move too far there. So the heat index was equal to 100. Now they want me to write a similar equation like this for when the heat index and the temperature are equal. So the temperature is the input. The temperature is T, and I want that to be equal to the heat index. And the heat index is the 0.0952 T squared minus 12.595 T. We're just replacing the 100 with T because T is the temperature, and this whole big equation is the equation for the heat index. Okay, so now I have the temperature equal to the heat index. All right, so I can solve this equation graphically. All right, And if I'm going to solve this equation graphically, I just need to see the original equation. And instead of y equals 100, I want to see y equals t, right? In the intersection there. Now, there are two. One of the intersections is at t equals 67.43 degrees, and the other intersection is at t equals 75.37 degrees. Okay. Now, both of these are a little low because they're below 80 degrees. We're going to say the 67 degrees is probably not going to be making sense in context, but the 75 one, even though it's lower than 80, it's close, it's closer. So we can state that at 75.37 degrees, it feels like, because the heat index is what it feels like, right? It feels like 75.37 degrees. So that's what it would mean if the temperature and the heat index were equal. It is what it feels like, even if you're at 90% humidity. Okay. Number 8. The National Weather Service does not calculate heat index unless the air temperature is at least 80 degrees and the relative humidity is at least 40 degrees. Based on your results in problems 5, 6, and 7, does this policy seem reasonable? Well, for number 5, we can certainly say that the 45 degrees did not make sense. And we can also say that the 85 and the 84, those ones did make sense. And we can also say that, the 75, there's no need to calculate heat index at that point because there is no heat index at that point. So it does seem reasonable. Yes, because heat indices don't really make sense below 80 degrees. And we have data to explain why they don't make sense. First of all, at 75, it feels like 75. So you don't need a heat index. That's part of why it doesn't make sense to go below. And then the 45, of course, saying 190 degrees, that does not make sense in context. So, all right. According to this policy, will the heat index reported by the National Weather Service ever be equal to the actual air temperature? Well, no, because the intersection points are at temperatures below 80 degrees. And those were the intersection points that we found a moment ago with the 67.43 degrees and the 75.37 degrees. Our intersection points t equals to h of t. They're not above 80 degrees, so they're not going to be something that would be reported by the National Weather Service. Okay. Very last example in this section, we have another data set. I stuck it over here already, so don't have to watch me type. I'm going to zoom out on it. And they would like us to decide if this is a good quadratic function. So here I see like maybe linear would have worked for those points, but this one down here makes a big jump and then it sort of like increases by a lesser amount. So I'm kind of seeing maybe an upside down parabola shape for this particular data set. So let's do our regression. Y1 approximately a x1 squared plus bx1 plus c. And so we would write down our model. This is P of t is equal to the a value down here for this model is negative 0.020 t squared plus the b model is 1.090 and the c value is 55.249. And so what they're asking us basically is like, did we get the regression right? So that matches this right here. So we can see we have the same thing. So yes, the model we got from regression matches this equation. So we're doing a regression, and they're giving us the method for checking that we have the right thing. So ta-da, we did our second regression here with a data set that could be represented by a quadratic function. Decent R-squared value on this one is 0.9849. It's not quite as high as it was in the previous example, but it's still very high. So this data set can be well modeled by the quadratic.